Hi, all. Welcome. Thank you. Welcome to the 6th annual 3-Minute Thesis Competition. I'm Scott Adler, and I'm Dean of the Graduate School. It's great to have you join us here today for one of my favorite events of the year. Now, the Graduate School at the University of Colorado Boulder is made up of nearly 6,000 graduate students in over 130 different programs. And throughout their time here, almost all do some kind of research or creative work, acquiring world-class expertise in their chosen fields as they train to become the next generation of teachers, scholars, artists, and researchers. They do this in part thanks to the generous support of our donors who fund the fellowships and grants awarded by the Graduate School each year. You hopefully have noticed the slideshow on the screen behind me highlighting some of our recipients, a few of whom are here with us today in the audience. So I want to take a moment and recognize their outstanding achievements. From astrophysics to dance, our graduate students are pushing the boundaries of their disciplines and with the guidance of our distinguished faculty, gain the necessary skills and tools to tackle some of the most complex and pressing problems of our time. One reflection of the excellence of our graduate students is that CU Boulder is among the top 10 universities in the number of students with NSF Graduate Research Fellowships, one of the nation's most competitive and prestigious fellowships for graduate study. And yet, much of the amazing research that they do flies under the radar and is only fully understood and appreciated by a small group of specialists within their discipline. That's not just a shame, but in many ways, it's a missed opportunity to advance the understanding of science, the value of research, and the remarkable scholarship going on here at CU. That's why I love the 3-Minute Thesis event so much. It's not only a way for us to showcase the incredible work, but also a wonderful opportunity for students to present an elevator pitch for their research. They do that by summarizing their sophisticated and sometimes obscure research and analysis in a way that's accessible for even a general and everyday audience. Now, learning how to do this is no easy task and requires training and practice. Starting last fall, 25 graduate students began a series of workshops to prepare for this competition. These workshops were focused on storytelling, writing, presentation skills, and even one on improv comedy techniques. As you can see, our 11 finalists competing today have worked very hard to get here. Their presentations are really fabulous. Now let me introduce our MC for today's event. My dear friend, Bud Coleman, is Roe Green Professor of Theater and Associate Dean of Faculty Affairs and Initiatives in the College of Arts and Sciences. Bud will introduce our judges and set the stage for the competition. Welcome, Bud, and thank you for being here today.
Absolutely. Thank you, Scott, and let me echo the Dean in welcoming all of you to the 3M competition right here at CU Boulder. The 3MT competition was actually founded in the University of Queensland in 2008. 3MT cultivates the students' presentation and research communication skills and challenges them to describe their research in 3 minutes to a general audience. To give you just a little idea of how challenging it is to distill an entire dissertation into 3 minutes, most dissertations average around 80,000 words. That would take approximately 11 hours to read. I'm not saying that all dissertations are not uninteresting, but 11 hours would take a long time. The popularity of the 3MT competition has grown over the years to include over 900 universities in 80 different countries around the world. The first place winner here in Boulder today will receive $1,500 in research funds and the opportunity to represent CU Boulder at the Western Association of Graduate Schools competition, which will be held this year in March in Portland, Oregon. Our runner-up today will receive $750 in research fund, and the winner of our People's Choice Awards will win $500 in research funds. The rules are very simple. A static single PowerPoint slide is permitted. No slide transitions, animations, or movement of any kind. No electronic media, no sound or audio files. No additional props, costumes, musical instruments, laboratory equipment. The presentations are limited to 3 minutes. If the candidate goes over, they will be disqualified. And the presentations must be spoken word, no singing or poems or rap. If you want to see a musical, you know where to go. Not here today. I would like to thank again the 11 brave souls, these graduate students, for accepting the 3MT challenge and for sharing their wisdom and passion with us this afternoon. On behalf of the graduate school and these amazing presenters, I want to thank you, our audience, who is here live for the first time in 3 years, and for our on-screen audience who are here via Zoom today, for your presence in helping to support intellectual inquiry, scientific discovery, artistic creation, and the dissemination of knowledge to the public. Now it is my great pleasure to introduce our incredible judges who are here today. First up is Teresa D. Hernandez, Director of the Athletic Program, Crawford Family Whole Student Athlete Program, and she's also a professor of psychology and neuroscience. Next up, Todd Solomon, President of the University of Colorado. Thank you, Todd. Next up, Siram Sankaranarayanan, Professor of Computer Science. And John Terr, CEO and President of the Boulder Chamber. The judges today will focus on 4 main areas in their evaluation of the presentations: comprehension, content, engagement, and communication. While we have our esteemed panel of judges, you, our in-person audience, and our virtual viewers at home also have the opportunity to vote on your favorites. So we have the People's Choice Awards. So take notes during the 11 presentations, and after the last candidate is done, you will have the opportunity to vote for your candidate. There will be a URL code on the screen at the end, and for those of you at home, you'll see a web address in the chat feature so that you can vote then. You'll have 10 minutes to vote. The focus of 3MT is storytelling in its purest form. One human being using the spoken word to introduce their audience to new ideas, new concepts, new ways of seeing the world. We are so glad that you're here this afternoon to sit around our fire and to hear what our community members want to share with us. The presentation order has been randomized, so first up, I'd like to invite Brandon Hayes. Brandon is a PhD candidate in mechanical engineering. The title of his presentation today is Powering Healthcare with Bubbles.
I research bubbles, which is a topic area that often has my grandparents wondering why I've been in school for so long. But bubbles are fascinating, and it turns out they're important in our everyday lives. They can be so thin that they distort light and form colors, like in a soap bubble. They're responsible for evenly cooking our pasta on a stovetop when we boil water, and they can even be used as a pump source to move fluid inside of a channel that's the size of a human hair width, which has been my research focus for the last 4 years. I'm in a field called microfluidics. Micro meaning extremely small, and fluidics, which is a study of how fluids move. And with microfluidics, less is more. Being able to shrink channels down to the size of a human hair width means that we can use less fluid and have more control over where fluid is being routed. This is what makes microfluidics exciting in healthcare. Imagine going in for a blood test and only needing a finger prick, or having an entire medical diagnostic laboratory fit into the palm of your hand, which is shown on the left. This is the promise of microfluidics. But we're not quite there yet. One of the key challenges is how do you move fluid from point A to point B in a channel that's the size of a human hair width? Well, my answer is with bubbles. In my research, I use bubbles as a pump source to move fluid inside of microscopic channels. What does this look like? Well, if we zoom in on just one microchannel on the handheld device shown on the left, the working principle is actually quite simple. I take a microchannel and I fill it with water, which is shown in blue. And then I place a small heater inside of this channel, which is shown in black. I use this heater to boil water and produce a bubble, which is shown in red, that then expands and collapses inside of the channel to move fluid. Repeat this over and over again, and you get a working micropump. However, it's a bit easier said than done. It turns out, in practice, this bubble only lasts for a fraction of the time it takes for you to blink, and is as small as a human hair width. This makes it difficult to study. And so in my research, I first started off by developing mathematical and computational models to understand how does the bubble form and how much fluid can it actually move. Next, I needed a way to study this system in the real world. So I developed a custom microscope setup to be able to photograph these bubbles at high speeds, close to 1 million frames per second. And I used this technique to measure how much fluid is being displaced every time the bubble forms. Now, up until this point in my research, I've only used water as the working fluid. I haven't used biologically relevant fluids like blood or urine, which are relevant in healthcare. So in the last phase of my research, I plan to study how do these micropumps behave and interact with biological fluids like blood. Hopefully, one day in the future, when we go in for a blood test, we're only going to need a finger prick, and we'll have bubbles to thank for that. Thank you.
Brandon.
Thank you.
So after each candidate's presentation, I'm going to do just a brief Q&A with them to give our judges time to make notes and for you to have an opportunity to get to know some of these amazing students. So our first question is, Brandon enjoys swimming and road biking. What are some of your favorite trails?
Yeah, like that was one of the draws of first coming out to Colorado, actually, from Rochester, New York. But going up Flagstaff or up to NCAR is kind of the key rides right now. Yeah.
Excellent. So I know that you're from Ohio. So I'm assuming you didn't do much mountain biking in Ohio. Is that true?
Actually, so I started doing triathlons at the beginning and then did start road biking in Ohio, and then it kind of blew up a little bit more when I came out to Colorado more than anything else.
Excellent. So I hear that you have a twin brother.
Yes.
Who's also a student here at CU?
Yep.
So did you make it a condition of accepting your grad position in the mechanical engineering program if they got to come along too?
Yeah, I don't think they would like if it worked like that. No, in that case, it ended up being more of a little bit of a fluke that we ended up at the same place, but it worked out overall.
And what is he studying?
So he does mechanical, he's right there. He does mechanical engineering too, actually. So both in the same field, but different research focuses and different emphases.
Well, I was going to ask if you're identical or fraternal.
No, you can guess.
Yeah, I can kind of tell. Thank you very much, Brandon.
Cool, thank you.
Next up, we have Yasmin Lopez. She's a PhD candidate in civil engineering, civil, environmental, and architectural engineering. The title of her presentation today is Evaluating the Value Proposition of Adopting Virtual Reality for Construction Safety Training.
the adoption of VR to enhance construction safety has been based on assumptions, not on facts, as there is no empirical evidence that VR improves the skills necessary for construction workers to make safe decisions at work. Therefore, my research project aims to evaluate if VR should be adopted by the construction industry to improve its safety performance. To do this, my study is concerned with answering three research questions. The first one being, does VR work? And if it works, why? And how does it work? To provide an answer to these questions, my research team and I developed a VR simulation from scratch. As you can see from the pictures on the top half of the slide, the feedback obtained from construction industry professionals allowed me to enhance the realism of the simulation and help me with designing a virtual environment reflective of a real construction site. But after developing the simulation, I still had to test it. And to do so, I followed the experimental protocol depicted on the bottom half of the slide, which starts with a baseline test of the skills necessary for construction workers to make safe decisions at work, such as hazard recognition and risk evaluation. Once this is done, participants complete a traditional classroom training session to then get tested. It's after this point that participants perform a VR intervention to then conclude the experiment with an intervention test. This will be the last piece of data I will need to evaluate the skill improvement that participants gain, if any, from my experimental protocol, which will not only allow me to evaluate if it works, but also to identify whether it works better as a standalone tool or when paired with a traditional classroom training session. My project is still in the development phase, but I expect my findings will not just help researchers to identify future areas of investigation, but also construction industry professionals to guide the adoption of VR for construction safety, which, thanks to my project, will be based on facts and not assumptions. Thank you.
Thank you. Thank you so much.
Up to the judges, if they feel like they need to judge.
Okay.
One for you right now.
Yeah. Oh, yeah, that's good. Thank you. So before Yasmin started her PhD program here at CU Boulder, she was the field inspector for a $130 million project at Midway Airport in Chicago. And I'm just wondering if anything happened during that time that that galvanized your commitment to construction safety.
Definitely. I fell in love with construction and at the time I knew that I wanted to go into graduate school. I just didn't really know exactly the path that I wanted to take. So when I found out that I really liked construction, I decided that I should be pursuing my degree instead of developing my professional career at the time. So that's what happened.
So I understand that you and your partner enjoy walking your dogs. Mm-hmm. So do y'all have some favorite paths that you take?
We like to go camping a lot. But as far as hikes, I like the Marshall Mesa Trail.
Excellent.
I like the view. It's pretty awesome. And not a rough trail,
no.
so.
So I have to ask, did you rehearse your 3MT speech to your dogs?
I did not, but if I win, I will to practice. Yeah, they'll be helping me out for the future rounds if I win.
Excellent. So we asked the contestants today to share some biographical information about themselves, and I'm wondering if you remember what you wrote for the entry about your favorite food.
My mom's. Yes. For my favorite food, I said that my mom's was just my favorite because regardless of what it is or where it's at, it always just tastes like home. So
And on that note, thank you.
Thank you.
Thank you. And next up, We have Ariel Lucas Arasso. He's a PhD candidate in molecular, cellular, and developmental biology. The title of his presentation today is VitroSeq, a new system to study transcription.
How many genes do you need to change to make a mouse that grows up without limbs? The answer is 0. You can actually just change one enhancer. That's because enhancers are the genetic power switches that turn on our genes. They're also specific, meaning in this mouse, only limb development is affected. The step of gene expression controlled by enhancers is called transcription. That's taking a piece of DNA and reading it to make your RNA. We think of proteins as the building blocks for all of life, and DNA as the place where we store the information to make our proteins. Well, RNA is the intermediate step, meaning no enhancers, no limbs. So how it is that enhancers communicate to genes is not totally clear, but we do know that enhancers are actually transcribed as enhancer RNAs. So this time, no enhancer RNAs, no limbs. And that is my hypothesis that I'm going to test with the system I'm developing called VitroSeq. The way it works, you take a piece of DNA, throw it into a tube with your proteins, those are in black, that will then transcribe your RNA, that's the yellow string. The innovation of VitroSeq is a biotin label, that's the B, that allows us to separate our RNA from our DNA and our proteins. With this pure RNA, we can now get information such as length and sequence and source. The last two are unique to VitroSeq. So far, I've used VitroSeq to transcribe an enhancer and a gene in separate tubes. Next, I will use VitroSeq to transcribe an enhancer and a gene together in the same tube to see, does the presence of my enhancer RNA increase transcription of my gene? Again, to get at the question, how is it that enhancers communicate with genes to turn them on? I think it's as enhancer RNAs. So, today, I've told you all about enhancers, which are critical for development and gene expression. I've also told you about VitroSeq, the new method I'm developing to study how enhancers communicate with genes to turn them on. So I hope that what we can do with the information we gain from VitroSeq is develop new enhancer RNA therapies that might be used to reverse some of the developmental defects like the one I've shown you here. Thank you.
Thank you, Ariel. Thank you.
I like your tie.
Thank you. I understand that you belong to 2 volleyball leagues. So I want to know how somebody in MCDB has time to be in 2 volleyball leagues.
Well, sleep is for the weak. You find that you actually learn a lot about biology from playing volleyball. One of the things personally that I've really taken from the experience of being in 2 leagues is collaboration, actually being able to communicate with your teammates, which is also critical for how we do science. You think I was able to do everything I showed you today by myself? No. I told me to stop talking.
No. No, keep going, keep going. I was agreeing with you.
Okay, sorry. No, I had a bunch of mentorship from people who were very kind to me, and I'm grateful to have all of them in my life. That was what I was going to say.
I did not mean to cut you off, not at all. Ariel, I know that one of your favorite foods are empanadas. So what are your go-to fillings for empanadas?
Okay, so from Argentina, love empanadas. The basic thing is beef, and we fill them with also hard-boiled eggs and what is the thing you make olive oil out of? Olives. But recently, living in Colorado, I've had to make a bunch of spinach empanadas because there are a lot of vegetarians here. And I've learned to make them pretty well. So those are the 2 that I make most often.
Well, that's excellent. Invite me over sometime.
Oh, absolutely.
So I understand you like rock climbing?
I do. I love rock climbing. It was like the first Colorado thing that I got into when I moved here. It's been a very fun time. You meet a lot of really kind strangers who will help you, again, grow and literally reach new heights.
Literally?
Yeah.
So do you do it in an indoor setting or outdoors?
Oh, definitely indoor. Like, I enjoy the rock climbing. I'm not looking to die.
And on that note, I think that's a good place to stop. Thank you, Ariel.
Thank you.
No death. Our next candidate today is Lexi Deal, a PhD candidate in chemistry. The title of her presentation is What Happens Between the Air and Water?
Why is the weather forecast so often wrong? Well, my work may be able to help answer that question. To introduce you to my work, I want you to imagine that you're in the ocean and you're wearing goggles so you can see that line where the water stops and the air around the ocean starts. Now I want you to zoom in on that line until you can see the individual molecules, and you've arrived at the picture that I have on the left. This is called the air-water interface. In the natural environment, organic molecules will concentrate at this interface, which is what I'm showing with the little black blobs. These molecules can come from both natural and unnatural sources, and even if there are only a few of them, they can have significant impacts on both weather and climate. However, because the air-water interface has so few molecules, it's typically not included in atmospheric models. In my work, I use a really cool technique called IRIS, which allows me to directly study the air-water interface. As I'm showing in the middle on the top, IRIS works by reflecting light off of the water surface, and that light tells me something about the structure of the molecules residing at the air-water interface. First, I examined how certain organic molecules will align themselves at the air-water interface. Using IRIS, I showed that even small changes in the structure of the organic molecules can dramatically alter their orientation at these interfaces, which is what I'm showing in the middle on the bottom. Second, we thought that because the air-water interface is in contact with the air, which has less water, we may be able to observe chemistry that doesn't happen when these organic molecules are fully submerged in the water. This part of my work is still ongoing. However, I do have some preliminary IRIS results that seem to indicate that we do see chemistry at the air-water interface that doesn't usually happen when these are in contact with water. Now, I use the ocean as an example, but really, these air-water interfaces are everywhere in the environment. And this includes on the surfaces of tiny water droplets in the atmosphere, as I'm showing on the the right. These droplets and the organics that coat them can have significant impacts on weather and climate. Some droplets and the organics that coat them will allow sunlight to pass through, which can contribute to warming, while other droplets and their coatings will reflect sunlight, which can prevent warming. And it's effects like these that makes the small things that I study have such a potentially large impact. By including my work into atmospheric chemistry models, we may not only get better at predicting the weather, but we may also be able to better understand how the climate is going to change. Thank you. Thank you.
Before coming to CU Boulder, Lexi was at Boeing for 4 years, including 2 years on a support contract on the International Space Station. What kind of work were you doing?
I used to like to joke that we were the janitors for the International Space Station because we made sure that the outside of the space station stayed nice and clean for all the researchers that wanted to put experiments up there.
And how does one keep it clean?
That's a good question. A lot of it is tracking materials before they go up there because it's hard to go and clean things off once it's there. So we had a long running list of all the materials that would go up to the International Space Station and how they would off gas and how that might deposit on surfaces.
Wow. Excellent. Well, thank you for doing that. Like Ariel, you like to do rock climbing,
I
right?
do.
So are you indoor or outdoor?
Both. Right now, since it's cold, I'm inside. But during the summer, it's nice to get outside a lot.
So have you run into Ariel yet?
No, I didn't know you liked rock climbing. We'll have to go together sometime.
Now, I admit I was surprised to read that your favorite food is...
Oatmeal. Well, it's one of those questions that I didn't know how to answer, but then I was thinking about it, and I've eaten oatmeal almost every day for a year and a half for my breakfast, so I feel like that kind of qualifies it as my favorite food.
So, what got you on that path?
Trying to have a more balanced breakfast, I think, so that I don't get I tend to snack a lot throughout the day, and so I
Well,
wanted,
I did a little research, and did you know that the Guinness World Record for the world's oldest family, who knew that was a competition, 13 brothers and sisters, their ages are 72 to 93, so that is an accomplishment. They credit their longevity to eating
Oatmeal?
twice a day.
All right. Lots of time to finish my research.
So you're on the right path. Thank you, Lexi.
Thank you.
Up, we have Alex Bradley, PhD candidate in chemistry. The title of his presentation is Air Inequality in Denver, Colorado.
The phrase, the wrong side of the tracks, was popularized in the 1920s, long after the establishment of the railroad as a staple of American society. It comes from the fact that neighborhoods downwind of railroad tracks are subjected to more soot and noise from running trains, and that the people who live there are generally too poor to live anywhere else. The railroad tracks in Denver, Colorado, run through the valley of the South Platte River, and there is a wrong side of the tracks in Denver. Today, this boundary is called the Denver Inverted L. It's a geographic area near the center of the city, the dashed white lines on the figures. People who live under the L are much more likely to be white, to vote, to have graduated high school, to have a more dense tree canopy around their home. Meanwhile, those who live to the north and the west of the L are much more likely to be non-white, to develop asthma, to have an income below the poverty line, and to have worse air quality. There are many factors that go into air quality, so we use a molecule called NO2 as a proxy. NO2 is a chemical that's a product of combustion from your cars, your factories, your power plants, and we can measure it from space using a satellite, which, after some data processing, results in the figure on the right. We combine our satellite data with traffic data, ground-based emissions data, and 2020 census data to give us more insight into why exactly people of color are subjected to more pollution. Highways, the train tracks of the now, have wrong sides too, and they're overwhelmingly populated by people of color. Additionally, 59% of people who live in Denver identify as non-Hispanic white, but only 47% of people who live near large emission sources identify the same. There's a historical and sociological reason for this effect too. For decades, people of color have been forced to live in certain areas of the city, be it from the effects of redlining, racial covenants, segregation. There's a reason why the neighborhoods with the most people of color in Denver are named after gold and silver smelteries that left the land harshly polluted. For instance, the Globe of Globeville or Swansea Smeltery. So we know who is affected the most and why. Our research is now turning from, is this a real problem, to what are we going to do about this? Other research has shown that location-based emissions reductions are the most potent in reducing pollution inequality, and for Denver, we agree. Specific emitters appear to be outsized influences in their communities. For example, a majority of people who live near Colorado's only oil refinery identify as Hispanic or Latino. So it's not going to be a cheap or easy fix, but we owe it to the most vulnerable portions of society to reduce pollution inequality. Thank you.
Thank you, Alex. So I understand that one of your hobbies is baking sweet treats.
I love sweet treats,
So
yes.
if you were going to invite us over this weekend, what might you fix for us?
This weekend, I'd make my go-to gingerbread cookies. It's my own recipe. My partner's grandmother said that they were the best cookies she'd ever had. And when someone's grandmother says that your cookies are good, done something right.
You are definitely doing something right. I also understand that you're a connoisseur of haunted houses.
That's true.
So in a non-COVID year, how many haunted houses would you attend?
So let me think. In the last space of time, Last October, we went to 3. We went to another one around Christmas time, and the next one is planned for 2 weeks from now. Valentine's Day Haunted House.
The things you would learn today. Who knew? Now, what do you look for as a quality experience in a haunted house?
Ooh, I like good atmosphere. So not just the scare actors. I like, well-painted and manufactured mechanical things that are jumping out at you. I'm not a big fan of jump scares, actually. I would prefer like gross out or a different kind of scare.
It's good to know. Now, I understand you grew up in Texas.
That's correct.
I did myself, and so I was not surprised to read that your favorite food is chili.
Yes.
What I was surprised is that, how do you like your chili?
So we eat our chili over pasta, Cincinnati style. I want to emphasize it is Texas style chili over pasta, not Cincinnati chili. There's a difference.
What is Cincinnati chili?
Cincinnati chili, Brandon might have a better, being from Ohio, you might know more about this. It's more of a sauce than a chili, really. It's got like ground beef, but it also has a bunch of different spices in it, but not typical chili spices. It's got like cloves in it, which I don't put in my chili. What I do put in my chili is a little bit of espresso as a secret for you.
Ah, so Brandon, is that? Okay. All right. Thank you.
Thank you.
Next up, we have Amanda White, a PhD candidate in astrophysical and planetary sciences. The title of her presentation today is Carl's Telescope Funhouse.
Astronomers learn things a little differently from other sciences. We can't just ask Jupiter to come down to the lab with us to run a few tests. In astronomy, the only data we collect is the color of the light that we see and the intensity, or how bright that light is. Just about everything we know about space has been learned from the color and brightness of light. And we've learned all sorts of things, like what a cloud of gas on Jupiter is made of, or how strong magnetic fields on the sun are. We can do this because light encodes the physical properties of what it interacts with within itself, which is awesome for physics. But it's also kind of a problem because the light is interacting with our telescope too. And what I do is help to determine what the light looked like before it entered the telescope. Now, I'd like you to imagine looking into a funhouse mirror. Maybe it makes your head really big and your torso super small, so your reflection is rather silly. The funhouse mirror is distorting the direction the light is traveling before it hits your eye. So that is a very exaggerated analogy to what's happening inside of a telescope, but let's explore the idea with Carl, the light particle in the upper right. As Carl enters the solar telescope on the slide, he's going to reflect off the first mirror and change orientation. Continuing through the telescope, Carl's going to get bounced around a lot. There are many pieces of glass between the sun and the mirror lab on the left. Like with the funhouse mirror, as light touches each part of the telescope, its orientation, or its polarization, a property of light we use to study magnetic fields, is going to change just a little bit. But that little bit is going to compound with each bounce. And by the time the final image makes it to our cameras, the polarization is much different than when it left the sun. The polarization is much different than when it left the sun. Oh my gosh. Thank you.
Come out. So before Amanda arrived in CU Boulder, she was at the Museum of Natural History in New York City. What is one of your favorite stories of working with meteorites there in New York?
I worked for the curator of meteorites, but I actually worked with comet samples.
Oh.
So I guess one of my favorite things about that was doing backwards ballistics, basically, because NASA has captured samples in a gel, and what we get left over is an impact trail. So that was always kind of cool to see what different materials would cause, how different tracks would form from different materials.
Excellent. Wow. So I know New Yorkers are very, very picky about their bagels. Where did you go for your go-to bagel shop?
I really liked a place in Park Slope that I happened to live next to, so it became a problem, called Brownstone Bagels.
And your favorite bagel?
I really like sesame bagels.
There we go. Yep. Now, I understand that you enjoy walking rescue dogs.
Yeah.
And what got you into that activity?
So I started by taking my own dogs to the trainer who runs the rescue. And I just kind of picked it up and enjoyed working with the dogs. They're a little short-handed because of COVID, so it was like, someone go play with our dogs. And it was, yeah, it was like, I get to give them their 15 minutes of individual attention, which is all they get, unfortunately. So it's really fun to do that.
So did you practice your speech to any of the dogs?
Yes, I did.
I love it. Today is Amanda's birthday, so I think we need to do a Concord version of Happy Birthday. Happy birthday to you. Happy birthday to you. Happy birthday, dear Amanda. Happy birthday to you. Bravo.
Thank you.
Our next contestant up today is Margarita Reza, PhD candidate in chemistry. The title of her presentation is Iodine Chemistry and its Role in the Atmospheric Ozone Destruction.
The signing of the Montreal Protocol in 1987, after the discovery of the Antarctic ozone hole, called for the phasing out of man-made industrial gases containing chlorine and bromine that destroy ozone. The ozone layer is very important for our global health as it protects us from UV radiation. So how is it doing? The good news is that ozone levels in the upper stratosphere are improving. However, ozone in the lower stratosphere is not recovering as expected. Iodine is not regulated by the Montreal Protocol, but it was considered in the 2022 Ozone Assessment Report. So where does it come from? Iodine is released from the oceans when ozone deposits into the sea and reacts with iodine in the water. It's also released by marine plant life. Ozone is important, and I'm going to tell you more information about that. What did I just say? I said iodine is released by marine plant life. And the important thing I want to tell you is that iodine happens to be much more efficient at destroying ozone than chlorine and bromine, as shown in the top left. So it destroys ozone in the gas phase and as it accumulates into particles. Therefore, investigating how it cycles between the particle and the gas phase is really important to assess its contribution to ozone depletion. So what did I do? I conducted some experiments where I coated a glass tube with an iodate solution. If we zoom into that solution, you can envision particles like what you see in the middle. They contain iodine, which I represented as purple dots, and iron, represented in red. The thing about this iron compound is that it is sensitive to light. We call these compounds photosensitizers. So when I shine light on it, I found that iodine gas was released from it. So I discovered key ingredients to a recipe that transforms particle phase iodine to the gas phase. And these include a light-sensitive iron compound and visible light. So how does this inform what happens outside of the lab? Well, we can find iron-containing dust particles in the atmosphere, and since sunlight is able to reach down to the Earth's surface, we can expect dust to play a role in the release of iodine, where it can destroy ozone throughout the atmosphere. We still have yet to determine if ozone destruction by iodine can explain why lower stratospheric ozone is not recovering as expected. But what we do know is that iodine concentrations are increasing due to ozone pollution. So iodine ozone destruction by iodine will continue to grow unless air quality everywhere is improved. Thank you.
Thank you, Margarita. Thank you.
Thanks.
So before coming to CU Boulder, Margarita taught high school chemistry and biology in Houston, Texas. So do you have a favorite story from your time teaching in Houston?
Oh, let's see. I think I don't have like a particular story, but I just found it really nice to get to see the students' excitement when there was a lab day, because they would see like everything out and they would have like their assignments, like who's the reporter and who's the equipment manager, and they'd be like, oh yeah, we're having a lab today. I'm like, did you do the pre-lab assignment? Because if you didn't do it, you're not gonna do it. So that was kind of fun to see them just excited about science.
I'll take that. So you like to cook.
Yes, I love to
So
cook.
now Alex told us we would get gingerbread if we go to his house this weekend. What would we get at your house this weekend?
Well, I would need more prep time, but if I do want to, you know, just feed my friends and people, I would make tamales.
Ah,
Yes.
and what kind of tamales?
So I've made vegetarian tamales. The green sauce is tomatillo based, and then the red sauce is like a dry chili based sauce. And then I use, it's like this meat substitute. It's really, really good. It looks like little chicken strips, but they're really nice in the tamales.
I'm coming over. That sounds great. So I understand that you like to collect earrings in your travels.
Yes.
So today you're wearing gold with some little...
They're little pizzas because,
I did not detect they are little pizzas.
yeah.
And so where are these from?
They're from my sister. I didn't travel anywhere, but they were a gift. But I was lucky enough to get some circular earrings that I should have worn today, actually, that I got at an art museum when I visited Finland. So that was really, they're really cute.
Oh, I think any day is pizza earring day.
You know,
So I understand that you have a cat. What's
I
her
do.
name?
Her name is Claudia.
And so did you rehearse your speech to Claudia?
No, but she was present while I was rehearsing, and every time I speak, Reiner, my advisor, can attest to this. She like, meow, like she will interrupt me. So when I was rehearsing, she would do that, and I'm like, okay, I got to do this in the office when she's not there.
Dogs are a better audience than cats.
Don't tell her that.
No, we won't. Thank you very much.
Thank you.
Next up, we have Rob Streeter, PhD candidate in electrical, computer, and energy engineering. The title of his presentation is A New Way to Measure Internal Body Temperature.
I'm working on a thermometer. Probably not the kind you're thinking of, though. It's not a glass tube filled with mercury, and it's not an infrared sensor like we've all had pressed up against our foreheads for the past 3 years. See, mine works by measuring very, very small radiation, which naturally occurs from all objects above absolute zero. I'll call this radiation thermal noise. Now, the power in thermal noise is proportional to the physical temperature of the object doing the emitting. The hotter the object, the more thermal noise. I can measure thermal noise with a very sensitive receiver called a radiometer, which is really just a piece of electrical hardware that converts thermal noise into an electrical signal that I can measure and analyze. Now, this is all fine and good when the object we're trying to measure is simple, like a cup of water, for instance. But let's take it a step further and think about something a little bit more complicated. Let's think about the layers of tissues between the forehead and the brain. Now, brain temperature is important for lots of reasons, ranging from simple fever monitoring to emergency cardiac repair surgery. The list goes on and includes the temperatures of many internal organs, not just the brain. Nevertheless, think of this stack of many layers, each layer contributing its own thermal noise to the measurement. Now, as you can probably guess, we've got a little bit of a problem. See, I'm only interested in the temperature of a single layer, say the brain, for instance. But I'm getting contributions from all these other layers, brain, bone, skin, all at the same time. Here's the really neat bit. If I know just a few things about each layer, namely physical thickness and a couple electromagnetic properties, I can build a model of all the layers. This model is really just a piece of software that takes that signal from the radiometer, as well as knowledge of the tissue layers, and uses it to determine the physical temperature of each individual layer. This new way of measuring internal tissue temperature, called microwave thermometry, stands to overcome lots of issues with existing temperature measurement techniques. For instance, needles and catheters can be used to insert temperature sensing devices, but that's invasive, and it takes a while to stabilize at a temperature. A popular alternative is magnetic resonance imaging, or MRI, but that's expensive, bulky, and limited to clinical settings. Remember the emergency cardiac repair surgery I mentioned earlier? The one where brain temperature was important? Well, it turns out surgeons have only about 30 minutes to complete the entire procedure, so every second counts. The technology I'm developing provides a fast, safe, and non-invasive way to determine the temperature of an internal tissue layer. This stands to revolutionize the measurement of temperature in the medical field and beyond. Thank you very much. I didn't forget.
Thank you, Rob.
Thank you.
So before coming to CU Boulder, Rob spent 12 consecutive months at the Amundsen Scott South Pole Station. How many people are there on the average, like in a given snapshot?
Sure. So it's kind of, you get 2 seasons down there, of course, because the sun comes up and down once a year. During the summer months, which is flipped from our time, there's around 180 people on station. But there were only 40 of us that stayed through the winter.
Wow. And I'm sure you have many powerful memories of those 12 months. Would you share one with us today?
Sure. So sometimes when you go down there, particularly if you spend the winter, you suffer from something called T3, or winter over syndrome. And I may work with you, bud, for 6 months, and then one day I'll wake up and I don't know your name. And I can't remember your name. And I suffered this. I was in a short trip to the bathroom, and I realized I didn't know where I was. I mean, I knew I was at the South Pole, but I don't know where I am in the station. There's 4 bathrooms. They all look the same. I'm lost. And it happened to me twice. And I go outside in the hallway. It's, oh, I know exactly where I am. But I could not, for the life of me. I'm going, come on, you're not stupid. You know where you are. Couldn't figure it out.
And how does one recover from T3?
I haven't suffered it since I've been back in the real world.
Good. Oh my gosh, that was scary. So I know you like to cook.
I do.
So Alex is going to make gingerbread.
Okay.
Margarita's going to make tamales. If
Okay.
we come over to your place, what would you serve?
Oh, that's a great question. Sounds like we've got a dessert. We've got kind of a main dish. I'll go for a chicken Caesar salad, and normally marinate the chicken ahead of time. A little bit of soy sauce and some spices. Marinate it overnight, and then serve it over lettuce and spinach mix with croutons, maybe even homemade if I've got the time, and pepperoncinis.
Oh my gosh. I don't know about you, but I am getting hungry.
Me too.
So I understand you also like running and hiking. What's your go-to favorite trails?
Oh, man, there's so many awesome trail running trails around Boulder. I actually really like the ones from Shanahan Ridge, because everyone goes straight to Chautauqua and runs from Chautauqua. Just go a little bit farther south, and Shanahan Ridge is right there, and no one ever runs there, and it's awesome.
It's our secret. Thank you, Rob.
Thank you.
Next up, we have Lydia Wagenknecht, PhD candidate in ethnomusicology. The title of her presentation today is, What Does Climate Change Sound Like?
All right, show of hands, who here knows their national anthem? Okay, now who knows the national anthem of Antarctica? All right, I'll give you a hint. It's ice, ice, baby. Totally kidding. Antarctica doesn't have a national anthem. However, national anthems are a great example of how music forms identity. The way that you sing or don't sing your national anthem can say a lot about how you position yourself in the place where you live. In my dissertation, I study how music and identity can develop during climate change. I do this by interviewing musicians and listening to music from Punta Arenas, a city in southern Chile. In the 1990s and early 2000s, Punta Arenas was known as the city beneath the hole in the sky due to its location beneath the Antarctic ozone hole. And that hole has shrunk now, but residents are still dealing with increased rates of skin cancer. So that's one way the climate crisis has impacted this community. Punta Arenas is also a major jumping off point for Antarctic climate research, which has picked up over the last 50 years. A large influx of researchers means that the culture and economy have developed to accommodate international travelers. So with all these climate-related developments, musicians have responded in a number of ways. Some use music to educate others about climate change. Others work to redefine community values in the face of this shifting population. And still others develop musical experiences to be consumed by international tourists and researchers. One example is electroacoustic duo Lluvia Ácida. This group records sounds from the region around Punta Arenas and Antarctica, and then synthesizes those sounds in soundtracks for documentaries about scientific research. By creating these soundtracks, Lluvia Ácida sonically reinforces relationships between Punta Arenas and the Antarctic research community. They mark their city as part of a larger polar community that has built a culture and economy around climate research. So the physical effects of climate change where you live might look different from Punta Arenas. But how might wildfires, flooding, or even a longer allergy season impact the ways that you consume or make music? Studying music helps us understand how we culturally process our world in the face of systemic crisis. And not only that, we can learn from Punta Arenas' musical communities to explore new opportunities for more effective communication on climate action. To save our ice, baby. Thank you.
Thank you, Lydia. Thank you. So before moving to Boulder, Lydia was teaching English classes in Lusaka, Zambia. So what came to be that got you to Zambia?
Well, I wish it was an interesting story, but really I graduated in 4.5 years, and I had like this 6 months, and this school needed teachers for English teachers, and so they needed like a short-term person, and so I went and I taught English.
Well,
yeah.
A lot of people wouldn't do that in their 6 months off.
Yeah.
Well, do you have a favorite story from your time there in Lusaka?
Ooh, that's a great question. I mean, I think honestly, I mean, this isn't a particular story, but I mean, as a music researcher, like obviously the musical part was like the most exciting, and I got to be part of a choir, and I made a lot of friends who, you know, taught me, like were really patient with me, like teaching me dance moves and like teaching me the correct like vocal styles, and so that was a really fond memory for me.
That's incredible.
Yeah.
So I understand that you like to run in the mountains. Where are your go-to trails?
Ooh, wow. I love so many. I think I really love, like, I would say my favorite like loop is like the High Lonesome Loop that's up in like Indian Peaks Wilderness. I love that loop. But I don't play favorites. Love them all.
So now Lydia doesn't just run. She has challenged herself to complete 3 ultra marathons. So please tell us, first of all, what is an ultra marathon?
Well, technically it's just anything beyond a regular marathon, which is 26.2 miles. But usually they come in distances like 50K, 100K, 100 mile, 200 mile.
And which ones have you done?
I've done a 45 mile, I've done 50 and 100 mile, yeah.
So what inspired you to challenge yourself in this way?
I guess like I'm just really drawn to it because I'm never quite sure if I can do it. And so I kind of just want to prove to myself that I can do it, and it's a really good, like I said, I love the trails and I love being outside, and so it's just like a really great way to keep myself accountable to like staying active and being able to enjoy those places. And
Wow.
yeah.
So how long does it take to run the 100?
For people who are fast, or for me, for people who are fast, can do it in like 20-something hours usually. I've only done one. I did it in like 35 hours, but I made the
You
cutoff.
made it.
Yeah.
You did it.
Yeah.
And on that note, thank you,
Yeah.
Lydia. Next up, we have Teddy Tortorisi, PhD candidate in physics. The title of his presentation is Novel Material Design by Trapping Machine-like Molecules.
Smartphones are faster, smarter, and smaller than ever before. Yet there's one component that continues to be stubbornly large. Phones receive signals from towers that need to be filtered in order to be legible. The signal is filtered by turning it into a sound wave and then back into an electronic wave. And the size of the filter depends on the speed of sound of the material used to send the wave. The slower the sound, the smaller you can make the filter. But atoms and solids are bound tightly together, so sound naturally rips through them very fast. In order to slow sound in solids, we need to devise a non-existent material which delivers sound through looser connections. I'm able to prototype such materials by combining molecules synthesized by my chemist collaborators. A host molecule forms honeycombs, which trap guest molecules in evenly spaced channels, providing scaffolding to hold them in place. The guest molecules are tiny machines like compasses, but instead of having magnetic needles that align to the Earth's magnetic field, these have electric needles that align with electric fields. Trapped in the honeycomb, the interactions between the needles force them to align, all pointing in the same direction. This is stable, so disturbing a needle causes it to flicker, and this flicker causes its neighbors to flicker, resulting in a slowly rippling sound wave. Previous efforts in characterizing these materials has been greatly limited due to the fact they're made as powders, which are poorly defined in many ways. So I've begun to evaporate the powder to grow thin films on small substrates as seen here in the top right. These films are so thin, you would need to stack 1,000 of them to be as thick as human hair. The surface image below zooms into about this human hair scale, where in the red circle we can fit well over 1 million honeycomb channels. The image shows the results of an incomplete film growth, revealing many honeycombs form separately and blossom out like snowflakes. This means that the films are not a perfect single honeycomb, but rather form a mosaic. However, other measurements show that the honeycombs actually align to the surface, forcing all the needles to spin on the same axis. This simple evaporation process shockingly has led to uniformity that allows me to know the number of compasses in a given volume, which enables me to quantify important properties previously out of reach. Not only does this research bring us closer to much smaller phone antenna filters by slowing sound in solids, but it also pioneers a new scheme to design, create, and test novel materials with desirable but never before seen properties. Thank you.
Thank you, Teddy.
Thanks.
So I understand that you're a wrestler and you know Brazilian Jiu-Jitsu.
Yeah, I would say it the other way around, probably.
Okay, well, explain for those of you who don't know what Brazilian Jiu-Jitsu is.
It's like wrestling, but the goal, instead of just pinning someone's shoulders to the mat, is to make them quit. So.
And what would that look like?
It usually involves like a joint lock or a chokehold.
Oh.
So, yeah.
I don't want to meet you in a dark alley. So how much Advil do you need after doing one of these bouts?
I typically don't use Advil unless I have a headache, so not often.
Okay, all right. So I understand you have an interesting story about the pronunciation or mispronunciation of your family name.
Yeah, I guess it's kind of interesting. So my family immigrated to the States during the time when so many Italians were coming over that the US started stopping people. And so they jumped from Sicily over to Tunisia in North Africa, which was a French colony. And so they changed the pronunciation from Tortorici to Tortorici to pretend to be French speaking, I guess, which I don't think that's very convincing. And then came from Tunisia.
Wow. Wow, I think it's interesting. So before coming to CU Boulder, I understand that you built cryostats for quantum information systems at NISTS. Now, I just read that like I act like I know what I'm reading. I don't know what a cryostat is or how you build one. So first of all, what is a cryostat?
So it's a vacuum system. So it's a big metal chamber, essentially, that you pull out all the air. And then it's got a refrigerator inside that uses helium as the what Freon would do in a regular refrigerator. And helium's liquid temperature is about 4 Celsius above absolute zero. And so you can use the refrigeration process with helium to get much colder than you can with any other method.
And so how does that work in a computer?
Well, so for quantum computers to work, you have to get them very cold. I didn't work with quantum computers. The quantum information stuff that I worked on was sending photons that were encoded to basically make crypto systems for cryptography.
Amazing. Thank you, Teddy. Next up, we have Dylan McGovern, PhD candidate in psychology and neuroscience. The title of his presentation is Weapons of Stress Reduction.
Post-traumatic stress disorder, or PTSD, affects 5% of the global population. This is roughly 400,000 individuals. To make this number a little bit more manageable, if we consider the city of Boulder, with a population of 100,000 individuals, it would take 4,000 cities of Boulder to capture this clinical population. And the truly devastating aspect of this statistic is this is only individuals who are diagnosed with the disorder. There are likely millions more people who fit this diagnostic criterion, but lack the resources or the privileges to seek care. And now I know what you might be thinking. This is a very bleak way to begin a presentation, which you're absolutely correct. But like any other disease state, researchers across the globe are studying PTSD and trying to learn what are clinically efficacious ways to treat this disorder. So there is hope, kind of. The issue with post-traumatic stress disorder is right there in the name, post-traumatic, after trauma. Clinical therapies and pharmaceutical interventions take place once the insult has already occurred to the body in a reactive way. My doctoral research aims to use a different approach. The experiments that I use test and ask the question, how can we immunize the brain against stress and prevent the formation of a disease state in the first place instead of attempting to manage its symptoms? And this is essentially what we've accomplished within our mice. Early in my research, I discovered cells within the brain's reward center that are very sensitive to stressors. And this might be unsurprising when you think about all of the rewarding aspects of our lives that are disrupted by stress experience. Using viral approaches, I was able to manipulate these cells within the brain's reward center and prevent any kind of stress deficit within our mice. These mice looked behaviorally identical to other mice who had never experienced stress in the first place. But the more interesting factor was that these mice were also protected against future stressors without any future manipulation being necessary. We had essentially created a stress-resilient behavioral profile. We had immunized these animals' brains against future stress insult. And yes, this is all very preclinical work and it's done in animal models, but I'm excited by this idea and this concept of designing drug therapies that can immunize us against future adverse events and arm our brains to be their own weapons of stress reduction. Thank you.
Thank you, Dylan.
Thanks, bud.
Thank you. So as you've heard, we've been doing public service announcements this afternoon to give people tips on where to go hiking.
Oh, God.
What are your go-to trails?
It's an excellent question. The really basic ones of like Chautauqua typically, but yeah. And I'm also not a runner to preempt that. So if you see me running, look behind me because something's chasing me.
Good to know.
There's a lot of runners in this crowd.
Now, I hear that you enjoy dancing.
I do, yeah.
What kind of dance?
Mainly club dancing, which is probably not what we're going to be doing here today.
No, I think we can do anything we want. So I hear that your favorite food is crab.
Crab rangoons, and I will die on this hill. They are the ideal food. They have every perfect combination of texture, sweet,
So-
savory, everything.
For folks who don't know what a crab rangoon is, what is it?
It's basically crab with a kind of sweet like cream cheese on the inside that's then fried. And usually there's a really nice sauce with it. Aloy Thai has the best crab rangoons in Boulder.
Oh, that was my next question, is where's your go-to place?
Oh yeah, I got them yesterday and I'll probably be getting them tomorrow.
Sounds good. Now, as if he was not busy as a graduate student enough, you are apparently teaching yourself Chinese and American Sign Language.
Yeah, it's a good time for literally no other reason besides I really wanted to do it. So, yeah.
The excitement of learning.
Oh,
I think we're all on the same page for that. Thank you, Dylan.
Thank you, bud.
And let's give another round of applause for all 11 of our amazing candidates. While the judges make their decisions, now is the time for you, our audience here in the room, and for our audience at home, to vote. So you get to vote for the People's Choice Awards. So the URL is here, and for those of you at home, you'll see in the chat the link so that you can record your vote. Remember, you have about 10 minutes to vote. Thank you so much for being here. Your support of graduate school and of these graduate students is really very important to us. We'll be back in about 15 minutes to announce the names of the winners. Until then, the magic wall will open, and there are refreshments on the other side of the wall. So help yourselves after you vote to grab an appetizer and a glass of sparkling cider. Thank you all so much. Dear friends, welcome back. Our judges have made their decisions. Feel free to stay in line. Feel free to sit and eat. We can do this all simultaneously. The graduate school at CU Boulder has nearly 6,000 students from all around the world, and you had a chance to hear from 11 of them tonight. Now take those 11 and multiply it by 545 to equal our population of 6,000 students. Now that is what I consider the definition of brilliance. 6,000 graduate students is a lot of really talented people right here in our very own community. Remember that our first place winner today will take home $1,500 in research funds and have the opportunity to compete in it's right here. They will compete in a conference in Portland, Oregon, the regional competition. Yeah, I know it's here. The runner-up today will receive $750 in research fund, and the winner of the People's Choice Award will receive $500 in research funds. It is now my honor to welcome back Dean of the Graduate School, Scott Adler, who will help me congratulate our winners today. Woo. And first up, if we can have a drum roll, please. Excellent. Our People's Choice winner is Lydia Wagenknecht. Yeah, come on up. Congratulations. Next up, drum roll please. Next up, our runner-up is Lexi Deal. Congratulations. And the winner of the Boulder 3MT first place winner is Rob Streeter. Congratulations. Congratulations to all of our winners, and a job well done for everyone who participated in all the workshops this year. Now I'd like to invite Dean Adler to do our closing remarks.
Thank you, Bud, for being an awesome MC again this year. I want to, of course, thank all of you for being here with us today and making the time. This is one of our signature events for the graduate school, so I really appreciate you being here. Of course, I also want to thank our 4 judges for making their time and their expertise available to us. I really appreciate you doing this, so thank you again. All of our contestants, all of our 3MT competitors, amazing research. Really incredible. It's astounding to see you be able to boil down all these years of work and research and your thinking and your analysis into 3 minutes. So really incredible job. Finally, of course, I want to thank the graduate school staff, the most amazing staff at CU Boulder. And in particular, Haley Herman, who's right back there, who worked with all of our 3MT competitors and arranged this event. So thank you so much, Haley. Thank you, Haley. Yes. So please enjoy the food and have a great evening.